On our last slide, we laid out the classic trade-off in the drone design, the endurance and the range of fixed wing versus the maneuverability and vertical takeoff of multirotor. This begs the obvious question: what if you don't think you have a choice? What if you could bring the strength of both of them? This is precisely where the hybrid and specialized UAVs come to play, representing the next wave of innovation in drone airframes. First, let, let's look at the most predominant of these designs, the fixed wing hybrid VTOL. VTOL stands for vertical takeoff and landing, and that's the key to its design. These aircrafts are engineered to solve a single bigger back drawback of the traditional wing drones. They possess vertical takeoff capability, typically using a set of dedicated lift rotors, just like a quadcopter. This allows them to launch and land in a confined space without any need for runway or catapult. Once a drone is in air and has reached a safer altitude, it transitions into forward flight. The lift rotor of often shut down or pivot, and a rear-facing propeller engages, pushing the drone forward like a conventional plane. At this point, it begins to leverage the extended range of fixed model because it is now using its wing for lift. This energy efficient skyrocket allows it to fly for much longer and cover a larger distance than multirotor ever could. This combination of feature gives the hybrid capacity for commercial operators. Imagine a mission to inspect an offshore wind farm. The drone, the hybrid drone, can take off vertically from a small surfboard, fly 15 kilometers out of the turbine, hover to perform a detailed inspection, and then fly all the way back to land vertically on the same board. The mission profile that would be impossible for either a fixed wing or a standard multi-rotor drone. Beyond hybrid, there are other specialized design that rethink the very concept of flight. A fascinating example is lighter than air. Instead of burning the energy to constant fight gravity, these systems use buoyancy-based lift, filling a large envelope with a gas that is lighter than air, such as helium, much like a modern balloon. This fundamental difference in how they stay aloft gives them a complex, unique set of advantages. This primary strength is, is an extended hovering capacity that is unmatched by any other types of aircraft. Since they float naturally, they can remain stationary over a target for an incredible long time. We are talking about days, weeks, or even longer in design. This is directly tied to their low energy consumption for monitoring. With lift can take by buoyancy, their onboard power is almost used almost exclusive for small adjustment in the position, running their sensor and communication. This makes them the ultimate platform for persistent, a long duration surveillance or monitoring tasks such as providing telecommunication cover over a large disaster area or tracking environmental change over a large region. So, as we see, the world of drone design is not limited to two. categories. Hybrid VTOL provides a versatile, best of the both worlds solution for complex mission, while lighter than air system offers unparalleled endurance for persisting monitor. These are these diverse design are all becoming critical component of much larger technology ecosystem. They are evolving from isolated flying mission into intelligence, interconnected nodes for gathering data within the broader work frame of Internet of Things. Let's explore the connection in our next slides.
We have explored the incredible diversity in the drone hardware from tiny insect-like MAV to large versatile hybrid. The true revolution however begins when these individual aircraft stop acting an isolated platform and start becoming interconnected node in much larger digital ecosystem. This brings us to the crucial role of autonomous drone within the Internet of Things, or IoT framework. The Internet of Things is the vast interconnected network of physical devices, from smart sensor on fridge to thermostat in our home, all communication and shared data to create a more intelligent and responsive world. So, when do autonomous drone fits into the picture? You can think this of them as the ultimate IoT sensor, which while most IoT devices are stationary, drones are critical component because they can move through three-dimensional space to collect data precisely when, where, and when it is needed the most. They leverage their agility to navigate complex environment, positioning sensor in places that are dangerous, difficult, or impossible for human to reach. Furthermore, their ability to fly high above the ground level abstraction provides them with a significant advantage in the line of sight communication, making them highly reliable for relaying data in areas with poor connectivity. This mobility makes them exceptionally powerful tool for data collection, especially for large-scale environment application. As the slide notes, this includes environmental monitoring and air quality assessment. For example, a fleet of autonomous drones could be deployed over a large agriculture region to monitor soil moisture level, providing farmers with a precise irrigation instruction and conserving a mass amount of water. Similarly, drone equipped with a specialized sensor can fly through an urban center to create dynamic 3D map of air pollution, identifying hotspot and providing city planners with actionable data to improve public health. This capacity extends directly into the realm of smart city application. A smarter city is one that uses interconnected technology to manage its resource and service more efficiently, and drones are becoming a cornerstone of this vision. They are invaluable for infrastructure monitoring. An autonomous drone can be scheduled to regularly inspect bridge lines and cell towers using AI-powered computer vision to detect small cracks, corrosion, or other signs of wear before they become critical failure. They also be used for energy efficient management. For instance, a drone with a thermal camera can survey a neighborhood at night to identify buildings with poor insulation, that are leaking large amount of heat, enabling targeted energy safety initiatives. The OpenCV logo seen on the slide is a node of software that makes this possible. It is a computer vision library that helps drone interpret and understand the visual data they collect, turn it into a valuable information for the entire IoT network. In essence, the autonomous drone are the mobile intelligent eye in the sky for the intelligence of things. They overcome the limitation of fixed sensor by bringing powerful data gathering capacity to any point in the physical world. This idea of single drone acts as a node in the network is powerful. But what happens when we take it a step further? What if the drone themselves begins to form their own intelligence? A collaborative network. This leads us to one of the most exciting and futuristic area of drone technology, the use of drones.
Our last discussion concluded with the introduction of dynamic observer theory, a powerful method for estimation that uses a model of system physics. Today, we'll focus on the most widely used implementation of that theory in robotics and aerospace, the extended Kalman filter. The extended Kalman filter is an extension of Kalman filter for nonlinear system. The original Kalman filter is a landmark achievement in estimation theory, but it has one major limitation. It only works for systems whose dynamics and measurement are described by linear equation. Unfortunately, the physics governing aircraft flight are highly nonlinear. The EKF is an indigenous adaptation that allows us to apply the power of Kalman filter to these real-world nonlinear problem. At its core, the EKF's purpose is to estimate the state of dynamic system from a series of noisy measurements. This is precisely the problem we need to solve for our MAVs. We have a dynamic system, the drone, and a series of noisy measurement from its sensor. And we need to produce the best possible estimate of its cruising, such as its altitude, velocity, and position. The key innovation of the EKF is how it handles the nonlinearity. Instead of solving the nonlinear problem directly, it cleverly sidesteps it. The EKF uses linearization around the current estimate to apply the standard Kalman filter. The diagram on the slide provides a great illustration of this process, which it is called as passing Gaussian through linearized approximation. Imagine the system has a belief about this current state, represented by the bell curve on the left. To predict the next state, this belief must be passed through a nonlinear function. EKF approximates these curves with a straight line, a tangent, its point of the current uh, best estimate. It uses this simplified linear model to project belief forward, resulting in new adapted belief about the state. Mathematically, the EKF handles nonlinear state transition and observation model through Taylor series expansion and Jacobian's matrix. The first order Taylor series is the tool used to create the linear approximation, and the Jacobian's matrix is the result of this process. This technique is not just an academic exercise, it is absolutely critical for the navigation, tracking, and control system. In fact, the EKF is widely used in MAVs, micro air vehicle, for state estimation. It is the workhorse algorithm that runs at the heart of the most modern autopilots, fusing the data from IMUs, GPS, and other sensors to provide a single, robust estimate of the drone complex state. Now that we have the highest level understanding of what the extended Kalman filter is, let's look more closer at how it operates. The EKF is specifically designed for addressing nonlinearity in system propagation and measurement model. This means it can handle both the complex physics of the drone motion and the nonlinear way in which its sensor relates to its state. The EKF accomplishes this through a step-by-step process: prediction and updation. The first phase is the prediction step. In this step, the filters use its internal model of MAV's dynamics to project the current state forward in time. It propagates the state estimate and error convergence using non-linear model and its Jacobian matrix, especially based on the last known state and the command sent to the motor. It makes an educated guess about where the drone is now and how it is oriented. Crucially, it also predicts it is now uncertain, known as the error convergence. It also it is also predict that it is perfect and uncertain will grow over time without new information. The second phase is the measurement update. This occurs when the new piece of the data arrives from the sensor, like GPS or an accelerometer. The filter then corrects the state estimate and, and a covariance based on the sensor measurement and the Jacobian of the measured model. It compare its prediction from the last step with the ac- accurate measurement. If the measurement is close to the prediction, the filter becomes more confident in its estimate and reduce its uncertainty. If the measurement is significantly different, the filter adjusts its estimate, weighting the new measurement against its predicted based on how noise it is believed the sensor to be. This constant cycle of prediction and correction is what allows the EKF to track the true state of the system over time. Both of these systems are made possible through the process of linearization. The EKF uses first order Taylor series approximation around the current estimate to create a linear version of non-linear model. This allows the powerful mathematics of the original Kalman filter to be applied. The filter is that provides a balance between computational efficiency and accuracy for moderately non-linear system. It may not be as precise as more advanced filter, but it is a highly efficient, making it perfect for the embedded processor on MAVs. The AHRS evolution diagram on the slide shows this practically. Early autopilot firmware like Copter 3.21 uses simple methods like TCM and inertia NAV. However, later version processed to use EKF1, EKF2, and now we are currently at EKF3, demonstrating the industry's wide adaptation and continuous improvement of EKF as the standard of MAV state estimation. Now that we have established the theory behind EKF, let's look at this first and the most critical application in the MAVs, altitude estimation. This is the process of figuring out the drone's orientation in space, which is fundamentally to all aspects of its flight. The primary application of this specific EKF is that it estimates the roll and pitch angle of the MAV. While some observers also estimate, yeah, the core task of stability is getting a fast and accurate reading of the roll and pitch angle. The variables that the filter is actively trying to figure out are controlled in what we call it as the state vector. For this task, the state vector typically includes roll, pitch, and their rate, which can be mathematically written as x equal to psi theta p and q multiplied by t. This means the filter is simultaneously producing an estimate for four values: current roll angle, current pitch angle, current roll rate, and current pitch rate. To produce these estimates, the filter intelligently combines the data from two different states. The model integration shows how it works. The EKF uses the angular rate measurement for state propagation. This means it takes the high-speed data from the onboard gyroscope, the P and Q rates, and uses them in predicting step to project the altitude forward in time. However, because gyros drift, this prediction alone won't quickly become uh, won't quickly become accurate. Therefore, the filter also uses accelerometer measurement as output equation. The accelerometer provides a stable, long-term reference to the direction of gravity. In the update step, the filter compass into gyro-based prediction to the gravity vector measured by the accelerometer and uses the difference to correct from any accumulated drift. The result of the is sensor fusion is majorly improving the accuracy over simpler technique. The EKF provide significant better estimate during accelerated flight compared to simple method. The simpler method that rely heavily on accelerometer can easily confuse during turn or fast forward flight because the force from acceleration combined with the force of gravity makes it difficult to know which way it is truly down. Because the EKF has a dynamic model, it can anticipate and account for this acceleration, maintaining a much more reliable altitude. estimate even in aggressive maneuvers. Yes, ultimately, this robust and accurate estimation is essential for stable flight control and navigation system in MAVs. Without a trustworthy sense of this own altitude, a MAV cannot simply fly stable or navigate efficiently. Having seen how the extended Kalman filter is applied to the altitude estimate, we can now expand its scope to the even more comprehensive task of full MAV's navigation. This involves not just knowing how the drone is oriented, but also where it is going, and what environmental forces are acting upon it. The application of navigating EKF is to estimate a much larger set of variables. It estimates position, PN and PE, ground speed, which is VG, course, which is mentioned by X, wind, which is mentioned by WN and WE, and heading, which is mentioned by the letter chi. This state vector is incredibly rich. It includes MAV's position in north and east coordinates, its speed and direction of travel to the ground, the north and the east component of west vector, and its yaw angle or heading. By estimating all these states simultaneously, the filter can build a complete picture of MAV's situation. This comprehensive estimate is achieved through a process that can be thought of as an advanced GPS smoothing. The filter integrates GPS position, ground speed, and control measurement like with a nonlinear propagation model. In this updated step, in this updated step, the EKF uses the measurement from the GPS receiver. However, in between these relative slow GPS updates, the filter uses its internal physics model driven by high frequency data from inertial sensor to propagate the state estimate forward in time. This process fills in the gap between the GPS reader and filters out the noise, resulting in smooth, high rate navigation solution. The enhanced performance of this approach is significant. The EKF produces much better navigation estimate than the simple low pass filter, especially in the dynamic missions. A simple filter on the GPS would be sluggish and lag behind the drone's actual movement, where the EKF's prediction model allows it to generate a much more responsive and accurate estimate during maneuvers. One of the most powerful features of this type of filter is its wind estimation capacities. By comparing the MAV's velocity through the air with this velocity over ground, EKF solved for the wind vector. This is a crucial capacity for path planning and energy efficient flight in outdoor. Knowing the wind allows the drone to fly more precise path and conserve energy. Ultimately, this sophisticated estimation enables robust autonomous navigation even in a challenging weather condition. Now that we have the robust state estimate, from our extended Kalman filter. The next logical question is how do we use the information to actually control the MAVs? This brings us to the fundamental design philosophy of modern autopilot, a technique known as successive loop closure. The principle of this approach is elegant and powerful. It involves designing multiple single feedback loops in succession rather than one complete system. Instead of attempting to create a single monolithic control that handles every aspect of flight time simultaneously, we break the problem down into a nested series of simple control loops. Think of it as a hierarchy of control. The innermost faster loop handles the most basic stabilization, and each successive outer loop gives command to one inside it. This cascaded structure is classic and highly effectively controlled strategy. The key that makes this approach work is concept called bandwidth separation. The rule is that inner loop operates at higher bandwidth, 10 to 15 times faster than the outer loop. Here, the bandwidth refers to how quickly a loop can react to changes. Innermost, which might be controlling the angular rates of the MAV, needs to be extremely fast to provide stability. The next loop out, which controls the drone altitude, its roll pitch angles, can be slower because it relies on the inner loop to handle the rapid fire stabilization. The outermost loop, which might control the MAV's position or altitude, can be slower still. This separation is crucial because it allows us to design and tune each independently. As the slower outer loop perceives the faster inner loop as a single, well-behaved system, they can simply command. The building blocks of each of these individual loops are known as compensators. A flight control typically uses PID or lead lag compensators. PID controllers are the workhorse of the control world. They calculate a control output based on current error, the accumulation of the past error, and predicted future error, allowing for a remarkable balance of responsiveness and stability. Increased sophistication of CPU used in flight controller as shown in the figure, depicting the evolution of flight controller has enabled more advanced implication of these control systems. Ultimately, this approaches simplifies design, tuning, and implementation while providing robust performance across different flight conditions. By breaking a complex problem into a series of manageable, simple ones, we can build autopilot that are easier to develop and more reliable in the air.
We have been discussing the complex way drones can collaborate and share data. Now, let's focus on one of the most powerful and social benefit application of that collaboration. The use of drone as flying base station. The fundamental concept is simple but revolutionary. We can turn a single drone or more often a coordinated swarm of code, into a temporary mobile cell tower that can be deployed anywhere in the world. The primary function here is providing communication service to the people on the ground. In our modern world, a loss of connectivity can be catastrophic. This can occur in remote rural areas that lack cell coverage. A larger scale temporary event like music festival where the existing network are overloaded are most critical in the aftermath of a natural disaster. A drone equipped with the right communication payload can fly to a designated area, establish a link to a satellite or a distance ground station, and then broadcast a reliable cellular or Wi-Fi signal down to the ground subscriber, creating an instant bubble of connectivity. This capacity is most vital in the context of disaster relief. As the slide slightly points out, this technology is crucial when terrestrial infrastructure is damaged. After a major earthquake, flood, or hurricane, the first thing to fail are often the power and communication grid. Cell phone towers are towers and fiber optic cable are served. This isolated surveyors, leaving them unable to call for help, and it cripples the ability of the first responder to coordinate their life-saving effort. In this scenario, a fleet of flying base stations can be a game changer. They can be deployed into a disaster zone and restore communication within minutes or hours or days. This restoration link is literally lifeline, allowing standard individual to contact emergency service, enabling rescue teams to coordinate their movements and provide a data link for damaged. The application for this technology extends across the entire field of public safety. For traffic management, the drone could be deployed over major highway accident to provide a communication link for the emergency crew and stream video for the situation back to the command center. In search and rescue or SAR operation, a drone flying high above the remote widened area can create a communication network for ground teams, allowing them to stay in constant contact in an area with zero cell coverage. All of this fall under the umbrella of emergency response. The ability to rapidly deploy an on-demand resilient communication network is a massive force multiplier of any organization responding to a crisis. In short, using drones as flying base station is fast, flexible, and powerful method for providing connectivity where and when is most needed. It is a potential life-saving tool in disaster scenario and an invaluable asset for public safety and logistics. The ability to efficiently deploy these swarms, whether for communication or other complex tasks, depends heavily on their underlying control structure. On our next slide, we'll look at the different ways a swarm can manage and control.
Now that we have introduced the design philosophy of successive loop closure, let's look at the concrete example of how it is implemented. This slide details the structure of typical PID, the lateral autopilot, which is responsible for controlling the MAV's roll and yaw motion to follow a specific path. The architecture is built around a fine inner loop and a slower outer loop. The inner loop is the roll altitude loop. As the name suggests, its inner loop controls roll angle, chi, and the roll rate, p. Its sole purpose is to achieve and hold a specific bank angle as quickly as accurately as possible. It uses the primary roll control surface, the aileron alpha, to do this. This loop runs at a very high frequency, constantly making tiny adjustments to make the MAVs stabilized at the commanded roll angle, detecting the disturbance from things like wind gusts. While commands to this inner loop is the course hold loop. This is the outer loop, and its job is to regulate course angle x. The course angle is actually directing the MAV is traveling over the ground. This loop is concerned with navigation, making sure the drone is flying towards its intended pathway. It achieves this not by controlling the ailerons directly, but by commanding the roll angle. For instance, if the autopilot determines that it needs to turn right to back on the course loop will simply send a command like roll to 20 degree to inner roll altitude loop. The fast, stable inner loop that executes this command precisely. This separation of duties is the essence of successive loop closure. For some more advanced fixed-wing aircraft, an additional optional loop might be included as side slip hold. This loop's purpose is to ensure the aircraft is flying cleanly through the air without skidding sideways. It uses rudder delta R to maintain zero slip beta if equipped, resulting in a more efficient and coordinated run. By layering these simple controllers, we create a highly efficient system. As the slide concludes, the nested loop structure provides stability and robustness against disturbance while maintaining desired flight path. A fast inner loop handles the immediate stability, while the slower outer loop focuses on the overall navigational goal. This elegant design simplifies development and tuning and results in a very robust autopilot. Just as we use a nested loop structure for a lateral control, we apply the very same design principle to manage the aircraft's longitudinal motion, that is, its pitch, altitude, and forward speed. This slide breaks down the components of typical PID control for longitudinal autopilot. The architecture is once again built around the fast inner loop and the slow outer loop, as shown in the block diagram. The foundation of longitudinal stability is the pitch altitude control loop. This inner loop controls pitch angle theta during the elevator. Its one and only job is to hold the aircraft nose at a specific pitch angle that is commanded by the outer loop. It runs at high frequency using the elevator to make rapid adjustment to maintain this angle, thereby providing the core pitch stability for the MAV. The next layer of control is the altitude hold using commanded pitch loop. This is the outer loop
and its purpose is to regulate altitude h by commanding pitch theta c. This is a perfect example of successive loop closure. If the autopilot determines that MAV is below its desired altitude, this outer loop doesn't command the elevator directly. Instead, it calculates the required nose up pitch command and sends that to the inner loop. A fast and stable inner loop then takes over to execute the command, causing the aircraft to climb. Controlling airspeed is bit more nuanced as the relationship between pitch and throttle changes depends on the phase of the flight. There are different airspeed control methods. Often, the autopilot is using commanded pitch theta c in climb and descent zone to manage speed while setting the throttle to full or idle. Conversely, it will be using throttle delta T in altitude hold zone to regulate speed, while the pitch is being used to maintain constant altitude. When designing a, and tuning these nested PID loop, engineers must consider several key design parameters. These include actuator saturation limit, a desired damping ratio, to control the responsive and principle of bandwidth separation to ensure the inner loop are always significantly faster than the outer loop they support. We will move beyond the simple idea of a remote controlled aircraft and explore the complex layered system that enables true autonomy. We will we have covered the entire stack of technology from the sensor that perceives the world to the algorithm that makes sense of the data, and finally to the advanced control and planning that allows a drone to execute complex mission on its own. Our journey begins with the foundation of all autonomous operation, the sensor. The drone's ability is to navigate and stabilize itself, starting with its inertial system. At the core of this is the inertial measurement unit (IMU), which typically contains two sensors. First, accelerometer are the fundamental device that measure specific force, which is the combination of aircraft's own acceleration and constant pull of gravity. By sensing these vector force, the drone can determine which way is down. The second component is the rate gyroscope, which is essential for measuring drone's angular velocity. It tells the autopilot how fast the drone is rotating about its roll, pitch, and yaw axis. This high-speed rotational feedback is the lifeblood of the drone's stability system. While the IMU provides the core of self-awareness, it needs external reference to navigate the world. This is where the broader suite of navigational sensor comes in. A magnetometer acts as a digital compass, detecting the Earth's magnetic field to provide the drone with a sense of heading or direction. However, this reading is susceptible to interference from the drone's own electronics, requiring careful calibration and mounting. Next, pressure sensor provides critical data for altitude and airspeed. An absolute pressure sensor or a barometer measures ambient atmospheric pressure to determine the drone altitude above the ground. Different pressure sensors, often part of a pilot's static system, measure dynamic pressure to calculate the drone's speed relative to the air mass, which is crucial for efficient flight and stall prevention. The sensor that truly unlocks long-range autonomy navigation is global position or the GPS. The GPS provides the MAV with an absolute position anywhere on Earth, which enabling the technology for further features like waypoint following and automatic return to home feature. It works by triangulating its position from the signal of least four satellites. However, the GPS accuracy is affected by factors like atmospheric delay and geometrical arrangement of the satellite, a concept known as dilution of precision. To operate where the GPS is unavailable, such as indoor or in dense urban canyon, drones are increasingly turning to camera-based or vision-guided navigation. By processing a video stream, a drone can track features in the environment to reduce its motion and build a map of its surrounding. A technique inspired by biological vision system found in the nature. Now, having this rich suite of sensor presents a new challenge. Every sensor is imperfect. They all suffer from noise, bias, and drift. This is why the next layer of our autonomic stack is state estimation. State estimation is the process of taking all this noisy, incomplete data from multiple sources and fuse into a single, accurate, and reliable estimate of the drone's true state, its accuracy, velocity, and position. The workhorse algorithm for this task is the extended Kalman filter or the EKF. The physics of the drone flight are non-linear, and the EKF is a powerful tool that can handle by using linearization around its current best guess to apply principle of optimal Kalman filter. It operates in the constant two-step cycle, a prediction step where it uses physical model to predict the drone's new state and an upset, where it uses tensor measurement to correct its prediction. This is particularly critical for altitude uh, altitude estimation, where EKF uses the sparse but drifty data from the gyroscope with the stable but noisy data from the accelerometer to produce a clean altitude estimate that is robust even during aggressive maneuvers. Once we have a reliable state estimate, we can finally act on it. This brings us to the advanced flight control. Drone operate using different flight mode managed by a state machine that switches control strategically depend on the phase of the flight, such as takeoff, altitude hold, or descent. The underlying control mechanism is a design philosophy called successive loop closure, where we create a nested hierarchy of simple feedback loop rather than one single complex controller. The fast inner loop handles altitude stabilization, while the slow outer loop handle navigation and altitude control. The building block of these loop is typically the PID controller, a robust compensator that adjusts with the output based on the proportional, integral, and derivatives of error signal. While PID is powerful and widely used tool, more advanced flight controller are also available. Techniques like linear quadratic regulator or LQR allows an engineer to design an optimal controller by balancing control effort against performance, while linear model predictive control or MCP can plan optimal control input over future time horizontal uh, future time horizontal, allowing it to handle complex constraints more efficiently. This finally brings us to the highest level of autonomy, motion planning. Once the drone can stabilize itself and follow command, it needs the intelligence to generate those commands on its own. Motion planning is the process of computing a collision-free path from starting point of goal. It's essential for navigating in complex military environment. Planner must be computationally efficient to run on the drone's limited hardware and robust enough to handle dynamic environment sensor uncertainty. This can even be extended to highly specific tasks like the structural inspection path planning. Here, the goal is not just to fly from A to B, but to compute a trajectory that keeps a sensor like camera oriented towards the surface to methodologically inspect for defects such as on the bridge or a wind turbine. In conclusion, an incredible capacity of modern autonomous drone are not the result of single breakdown, but rather the seamless integration of these many technological layers. It begins with a diverse suite of sensors providing a rich multimodal view of the world. The raw data is then refined into coherent picture by sophisticated state estimate algorithm like the EKF. The clean state estimate is fed into hierarchical control system that provides robust stability and command following. And finally, intelligent motion planning algorithm use this capacity to make their own decision navigating complex world to achieve their mission goals. It it is this complex stack from sensing to planning that truly define the state of art in advanced drone operation.
In our last slide, we focused on how a drone can be used an array of sensors uh, to perceive and avoid external obstacle in its path. That is one half of the physical system's equation. The other half is internal. How does the drone maintain its own stability against invisible forces like gust of wind or air turbulence? The answer lies in the gyroscopic stabilization and the sophisticated sensor at its heart, the inertial measurement unit, or the IMU. The ultimate goal of this internal system is to achieve smooth flight. A multirotor is an inherent unstable aircraft. Without constant microscopic correction, it would immediately flip over and fall. The stabilization system primary job is to provide its stability, allowing the drone to do everything from capturing smooth video to execute a perfect stable hold. It must constantly counter external forces to maintain its position and orientation as commanded by the pilot or the autonomous flight command. The core component that makes this possible is the ILA. This is the tiny chip on the drone's main circuit board that acts as its sensor stars, much like in our inner ears. The IMU function is to measure any changes in the drone's orientation along the three axes of flight: pitch, roll, and lift. Pitch is the forward and backward tilt roll in the side-to-side tilt, and yaw is the rotational left or right. The IMU typically contains gyroscope to measure rotational changes and an accelerometer to measure linear motion. And by fusing the data from these sensors, it is its exact orientation in the space at all times. This constant stream of orientation data is fed hundreds or thousands of times per second to the flight control, which is the drone's central brain. The flight controller's job is to maintain the IMU data to make continuous micro adjustment to the motors. For example, if a gust of wind hits the drone and the IMU reports a slight unintentional roll to the right, the flight controller immediately processes this information. It then sends a command to the motor on the right side to speed up the motor on the left to slow down and generate a counterforce that brings the drone back to the perfect line. This entire sense process act loop happens so quickly that the drone appears to be perfectly still, even in a breezy condition. In short, the IMU constantly senses the drone's balance, and the flight controller constantly uses their information to make tiny connections that help in stability. This internal stabilization is the fundamental bedrock upon which all these drone capacities are built. Now that we cover the system for physical safety, we must turn to the other major area of digital threat. Our next slide will explore the cybersecurity vulnerability inherent in the drone network.